Hello everyone, this is Amit Prambar again, and we are going to continue on chapter 18 for CS110. Okay, let me go ahead and share my screen again. Okay, so we were at halting problem 4 of 6, constructing a new program that takes a program example as both program and data. Just to recap, we were talking about halting problem and proposed program for solving the halting problem. And here were the previous slides where we had proposed different kind of programs that takes in program example and sample data and solves the halting problem. And output is also loops in both of those slides. So let's proceed to slide number 4. We take a hypothetical halting solver and build a new program called new program. This program uses the target program example as both its program input and its data input. New program is designed cleverly. It runs on a hypothetical solves halting problem on example, and then it behaves in the opposite way of what the solver predicts. If the halting problem says that the program halts, the new program deliberately enters an infinite loop. If solves halting problem says program loops, the new program halts immediately. This construction setup sets up a contradiction by forcing the solver to be wrong in at least one case. We show how such a solver cannot exist. The slide demonstrates classic proof technique in computer science, proof by contradiction. We now feed the new program into solves halting problem as both its program and its data. Two outcomes are possible and both lead to illogical results. First, if solves halting problem outputs halts, then new program must loop forever, but that means the solver's answer is wrong. Second, if solves halting program outputs loops, then new program halts immediately, making the solver wrong again. In either scenario, the solver fails. This contradiction proves that no universal algorithm can correctly determine halting behavior for all programs and inputs. This result is one of the most profound limits in computer science, showing that some problems are fundamentally unsolvable no matter how advanced the computing becomes. The final diagram, where we see how construction of new program has programs, program example and program example as input, and then the new program has two parts. The new program uses algorithm for solving halting problem to produce output, and halts loops as a loop, and output is halt output for the new program. Here, the slide represents diagram showing the full circular structure of new program feeding into solves halting problem. The diagram visually reinforces how the constructed program forces the halting solver into an impossible situation by creating a case where the solver must always give the wrong answer. We prove that a universal halting problem solution cannot exist. This slide wraps up the halting proof and illustrates a deeper truth. There are inherent limits to computability. Some questions cannot be answered algorithmically. This discovery forms the foundation for modern computability theory and marks one of the defining achievements of Alan Turing's work. Classification of algorithms. Here, discussion of algorithms classification, we would be looking at polynomial time algorithms. These are the ones that running time can be expressed as polynomial function of the input size, such as n, n squared, or n cubed. These are considered efficient and practical. The set of all problems solvable in polynomial time by a single processor is known as class P. In contrast, NP complete problems are problems that can be solved in polynomial time if you have access to as many processors as you want. Essentially, unlimited parallelism. These problems are extremely challenging because while it is easy to verify a solution, finding the solution may require enormous computational effort. This slide sets the stage for understanding one of the most famous open questions in computer sciences, whether P equals NP. Let's recognize our bins, combining all polynomial algorithms in a bin labeled class P. The diagram helps visualize how problems are grouped based on their computational difficulty. Class P represents problems we can solve efficiently with current computing models. This organization highlights the difference between tractable problems, those that scale reasonably well, and intractable problems, which may require exponential or factorial time. Understanding this classification helps developers choose techniques appropriate for the problem at hand. Avoid brute force methods when dealing with computationally explosive tasks. Class P, Class NP, exponential, factorial, and unsolvable. This slide adds category of class NP to the diagram. NP contains problems whose solutions can be verified in polynomial time. Even if finding the solution may take far longer, the critical question is whether every problem is NP is also in P. If P equals NP, then all problems with efficiently verifiable solutions would also have efficiently computable solutions. This would revolutionize fields like cryptography, logistics, biology, and optimization. However, most researchers believe P is not equal to NP, meaning some problems are inherently hard to solve even though their solutions are easy to check. This slide highlights the deep divide between what computers can do efficiently and what may remain computationally infeasible. Herak 25. This slide highlights tragic real-world example of how software errors can have deadly consequences. The Therac 25 was a radiation therapy machine used in hospitals in the 80s. Due to software flaws in control system, the machine delivered massive radiation overdoses on several occasions, resulting in the deaths or serious injuries of 6 patients. The accidents were caused by a combination of insufficient testing, poor design assumptions, and inadequate attention to safety critical requirements. There were also failures in communication between engineers, operators, and regulatory bodies. The Therac 25 disaster underscores the importance of rigorous engineering practices, formal verification in safety critical systems, and thorough testing. It remains a powerful lesson in the ethical responsibilities of computer scientists and engineers. So, who am I on this slide? It represents uh, It shows a historical figure and poses several questions. What machine and award are named after this person? Why did Time magazine list them among the 100 most influential people of 20th century? And why did they die before the time? The slide refers to Alan Turing, a pioneer of computer science. The Turing Machine and Turing Award, often considered the Nobel Prize of Computing, are named in his honor. Turing was celebrated for his foundational contributions to computing and for his code-breaking work during World War II. Tragically, he died at age 41 following persecution for his sexual orientation. This slide invites reflection on Turing's legacy and the importance of ethical treatment of those who advance human knowledge. Do you know? A series of thought-provoking questions that encourage us to connect computing limitations with real-world issues. Why did journalist Julia Engwin wondered whether privacy has become a luxury? A concern reflects how digital footprints, online tracking, and online brokerage have made privacy harder to achieve unless one has the resources to actively protect it. The second question raises a practical warning. Tweeting about your vacation can signal that your home is unoccupied, creating security risks. Next slide asks what Watson is. Beyond being a Jeopardy champion, Watson is also a sophisticated AI system developed by IBM, capable of natural language processing and data analysis. Another question references a university where students hacked into graduate admission systems, highlighting ethical and security challenges in academia. Finally, Dijkstra's criticism of term bugs reminds us that many errors stem from poor thought processes and not random accidents. Each question invites deeper reflection on computing's societal impact. What is a microtangent? How is it used? They are tiny encoded particles added to explosives, inks, or products to aid in forensic tracing and counterfeit prevention. The Bletchley Circle, a television series about women who worked at Bletchley Park during World War II using their analytical skills to solve crimes. You would respond to an email from Captain Roy reminding us of how phishing scams often mimic authority figures to lure victims. The final question asks about traveling salesman problem, a famous optimization challenge seeking the shortest route through multiple cities. These questions reinforce diverse always computing intersects with security, entertainment, ethics, and complex problem solving. The concluding slides invites us to reflect on major themes on chapter 18. Throughout this chapter, we explored many limitations, shape of computing, limitations in hardware precision, software reliability, communication accuracy, algorithmic efficiency, etc. We also examined fundamental limits imposed by computability theory, such as halting problem and the boundaries of polynomial time computation. These constraints do not diminish the power of computing, rather, they help us understand how to design better systems, avoid unrealistic expectations, and apply careful engineering judgment. As we move forward, appreciating these limits enables us to build more reliable, ethical, and effective computational solutions. All right. I hope you enjoyed the presentation, and I hope you can go through all of the slides that are part of this chapter and do the required readings on it. If you have any questions, you know how to get to me, and I'm looking forward to having a productive student engagement session with you every week. All right, see you then. Bye.